Thank you so much for the invitation to come here and tell you a little bit about Kilonovae. So I want to start with a definition of terms. So Kilonovae are radioactive transients that are powered by our process decay. So, as we saw, the R process starts in its early phases by synthesizing a lot of elements that are extremely neutron rich and unstable. And so those have to decay back down to stability. In the process of that decay, of course, they release radioactive energy. And this radioactive decay is happening in the context of an explosion because you have two neutron stars merging together, or perhaps some other event happening that is going to unbind some mildly relativistic outflow that creates the conditions, namely neutron richness, that are necessary for the R process to proceed. And then as this cloud expands, it's getting heated by radioactive decay once those heavy elements are synthesized, and that's going to cause it to glow. And that is the electromagnetic transient emission that we were able to observe in the case of GW170817, and that hopefully we will be able to observe again as advanced LIGO and Virgo move towards their fourth observing run. So, Kilonova is kind of a blanket term for well, the terminology here is a little bit under debate, but I would say it's safe to consider it a blanket term for any radioactive transient that is produced in the merger of a neutron star with another neutron star or with a black hole. You can get different flavors of Kilonovae, and that's just because in these kinds of compact object mergers, you can have different manners of ejecting mass. So kind of three principal ones are here, but there are even more subtle variations that I won't go into. You can have material that is ejected through tidal stripping as a neutron star completes its in spiral prior to merger. You can also have outflows from accretion disks that are formed around the central merger in the aftermath of the merger. And finally, you can have dynamically squeezed ejecta that's liberated from the system right at the moment of coalescence. So all of these different environments give rise to slightly different patterns of nucleosynthesis, and that can affect the emission that we see from Kilonovae. But in all of these cases, you're expected to get at least some kind of R process, and so that's going to give you, some kind of Kilonova electromagnetic emission. Okay, so Kilonovae actually touch on sort of two nuclear science goals that maybe exist at like opposite ends of the like opposite ends of the spectrum of physical scales, maybe. So, one is it tells us about astrophysical nucleosynthesis. So like what nuclei are being made and how are they being, how are they decaying and what are the properties of the nucleosynthesis. But it also can help us understand mass ejection, which is mediated by the structure of neutron stars. So it helps us understand, nuclei, both small and large, because if we can understand mass ejection in these mergers, we can better understand the neutron star equation of state. But of course, all of these advances in meeting these science goals is predicated on having a very robust way to interpret the emission that we get from Kilonovae. So since this is a quick overview, I'm just going to focus on kind of two major ways that the details of the R process affect the emission that we see, but I'm happy to talk about it in more detail during the discussion or later in the meeting. Okay, so the first is that obviously the R process synthesizes the material that sets the opacity. So in the context of a radioactive transient, the opacity is just is the property of the gas that determines how easily light at different wavelengths can escape, right? So we know that certain species that may be produced by the R process have a very high opacity, and that happens to have a pretty strong effect on the emerging signal. Okay, so that's what you can see here. These are the results of radiation transfer simulations of Kilonova emission. So I'm showing, this is bolometric luminosity. So for people who aren't astronomers, that's just the total amount of energy as a function of, or total amount of energy per unit time that emerges as a function of time. And then to get a more detailed picture of the emission, I'm also showing spectral snapshots. So this just tells you how the emission is distributed among photons of different energies. And these are all, as I said, synthetic Kilonova models that were calculated or an ejecta that differs only in its composition. So the same mass, the same velocity, the same density profile, but what we're changing is the content of these high opacity species that can really have a strong effect on the spectrum. So as you can see, when you increase the content of lanthanides and actinides, thereby increasing the kilonova opacity, you get longer, dimmer light curves, and you also get spectrum that are pushed towards redder wavelengths. So you can see there's a pretty strong difference between like this minimally lanthanide enriched curve, or I'm sorry, this black curve, which corresponds to minimal lanthanide enrichment, and these much redder curves. So just a note here, that's kind of a broad brush way of thinking about the emission, right? We say, do we get something dim in red or sharply peaking in blue? And that can maybe roughly give us a handle on the total lanthanide and actinide content. The next level would be to develop diagnostics that would allow us to make abundance measurements, or at least put some constraints on the abundances from absorption features in the spectra. So that's similar to what is done in supernovae. You can associate particular absorption features with particular atoms or ions, and that can be a very useful tool. That's something I think with regard to kilonovae that is still in its infancy, but hopefully if we continue to observe a lot of these, and maybe when some new observing facilities come online and we're able to get more detailed measurements over a broader range of timescales, we can move towards doing this kind of analysis. Okay, so the second way that the R process affects the kilonova emission is that it sets the luminosity budget of the kilonova. So as I said, all of the energy all of the energy that we observe as the kilonova originates as energy from radioactive decay. And kind of the relationship between the emerging luminosity and the energy input is illustrated in this little cartoon here. You have some energy being input from radioactivity. Only some of that energy is effectively converted into the thermal photons that we observe as the kilonova. So the emission from the kilonova exists at optical and infrared wavelengths, whereas the radioactive energy input into the system, of course, is going to be the much higher energy radioactive decay products. Thank you. And so, it's this thermalized energy that kind of sets the budget, the luminosity budget for the kilonova, and the light curve tracks that, especially at late times. Okay, this is probably a little bit redundant for this audience, but this is just like an astronomer's summary of what the relevant nuclear, or what some of the relevant nuclear physics uncertainties are for kilonova modeling. And this is more just, a reminder of the excellent review of this topic that Rebecca gave. So I think rather than going over all of these in detail, the thing I want to point out is just that, there are kind of two categories of uncertainty. So one of these are, maybe we can think of them as known unknowns. So, their nuclear properties or certain reaction rates or treatments of fission where we don't know what they are, but there is a single right answer, right? Each nucleus is only going to have one mass, and if we can nail that down, that's really going to reduce our uncertainty. But the second source of uncertainty goes back to this idea of different mass ejection mechanisms in different astrophysical environments that might be produced post-merger. So even if we had perfect knowledge of nuclear physics, we still have some diversity in merging systems. That's going to lead to different thermodynamic conditions in the gas that's undergoing the R process. And that is going to lead to some variability in the R process as well. So both of these categories of uncertainties are important things to think about when we're modeling kilonovae. Okay, and so I will just show you one example, one kind of extreme example of how uncertainties in nuclear physics can really impact our ability to make inferences about kilonova ejective properties from light curves. So this again is similar to a plot that Rebecca showed. It's for a set of models that adopt different assumptions about kind of unmeasured theoretical nuclear physics properties. We used the PRISM software for each of these models to calculate the total heat that was released, and then we actually modeled the thermalization of that radioactive energy to come up with an effective heating curve. So that's what's shown here. This is just the energy that's available to power a kilonova for a single choice of mass and velocity if nuclear physics is allowed to vary. Okay, and the most important thing to notice about this is just the variation that you get, more than an order of magnitude in some cases over kilonova timescales. So not surprisingly, that has a pretty large effect on the light curves if you are, putting very different levels of power into your ejecta, your light curves are going to look very distinct. So again, this is for a single kilonova mass and velocity. I'm also showing the let's see, the mass fraction of lanthanides and actinides for each model. Yeah, and I think the thing to just make note of here is that, clearly once you allow nuclear physics to vary, you can get a lot of diversity, and that makes it harder to make progress on the questions that we'd like to use Kilonovae to make progress on. Okay, so one example, as Rebecca mentioned, that I will just mention very quickly before I move on to my summary slide, is that at late time we know that fission can dominate late time heating. So that's a case where that's a case where you have a smaller number of decaying nuclei. Things are a little bit simpler. So if we can get a handle on what fissioning isotopes might be produced that have long half-lives, we can use that to constrain compositions and to better understand actinide production and fission in Kilonovae. So finally, this is just a summary on some recent progress in understanding Kilonovae, and I think I'm at the end of my time, so I'll just leave this up here and happy to talk more or take questions. Thank you.
Thank you very much.